Stealing reference books from the FBI library. And for what joyful purpose?
Looking for anomalies. Look at this box. And I can recreate exactly what happened on some sunny summer day back in 1947. It's like the numbers talk to me. They comfort me. They tell me that even though lots of things can change, some things do remain the same.
Hello and welcome everyone. As you saw in the introduction, we are going to dissect Fox Mulder's love for data and stats. Just kidding, we are covering Exploratory Data Analysis or EDA. This is a method developed by John W. Tukey. According to him, EDA is about looking at data to see what it seems to say. Just focus on simple arithmetic and visuals to uncover new insights. It concerns with appearance and not confirmation. I have the link to John Tukey's book in the description below. Also, Packet's hands-on exploratory data analysis with Python is another good resource to have for EDA. I'll leave the link in the description below. There is no formal process for EDA, but we can use descriptive statistics to perform EDA on a dataset. EDA is a process of examining a dataset to discover pattern, spot anomalies, detect outliers, and check assumptions. We will go through examples that cover these topics, so stay tuned. EDA exposes its users to a variety of techniques to look at data effectively. It helps you create new hypotheses. So the big question is, where does EDA fits in the data science or data analytics process? EDA comes in after you have defined your overall objective for a data analysis process. You have identified your sources for data, collected and cleansed data. But before you go through the formal modeling process, you can perform EDA to better understand your data. It's a detour from the normal process. What can you learn about your data by summarizing and visualizing it? Or what data has to tell us if we want to throw some simple calculations or visualization at it? This is the basis of EDA. I'll be working with AdventureWorks data extract. If you have been following the channel, I use this data set. It's available in the GitHub repo in an Excel file. A link is in the description below. We will use this dataset and put it through the EDA lens. I'll be using Python to carry out the EDA process. What is the outcome of EDA? It helps us discover anomalies, pattern, and trend. It helps us understand and enrich our data. During the process, we may find out that we need additional variables. We can perform feature engineering to create new features that enhances the usability of our data. The data exploration may help us decide what model to choose that best fits our data. By visualizing the data, we come up with new ideas and our hypotheses that were not apparent before. This is where EDA fits in the overall scheme of things. For EDA, we'll be using the following methods. We will use descriptive statistics, uni and bivariate analysis. Under descriptive statistics, we will look at data distribution, and we will fit a normal distribution to our data, check the skewness of our data. We will check the summary stats of numeric columns in our data. These stats will help us with the data distribution and to detect outliers. Now we have a clear picture of EDA and where it fits in. Let's explore our dataset. We will use Jupyter Notebook. Complete Notebook is available on the GitHub. Link is in the description below. At the top, we import the required libraries. We'll use pandas to import, clean, and transform data. For visualization, we'll use matplotlib and Seaborn. To test distribution and find correlation, we'll make use of SciPy. Also, I am using the magic function to print the visualization inside the notebook. First thing first, let's bring in the dataset. I have the file downloaded in the current directory in a folder called data. With the help of pandas read_excel method, we can read the Excel file, save it into a variable called df. We can see the top 5 rows with df.head method. We can also print last 5 rows with the tail method. This displays the data frame. We can see all the columns and what kind of data they hold. We can also check the data type of each variable. We mostly have objects and one date time, and rest of them are float types. These are the numeric variables. We can print out the column names of our data frame. Now let's start with the EDA steps. We are going to focus on few variables and drop the rest of the columns. So if you have a large data set, it's a good idea to narrow it down. We are passing list of columns in square bracket to the data frame and saving it in a df variable. Let's call the head method to see the revised data frame. Next, we are going to clean up the columns or variable names. Pandas has a built-in method called rename, and we are passing it columns with old and new names. I will run this cell and our column names are updated. Okay, let's go over some terminology. Data frame columns in data science world are referred to as variables and or features. I may refer to them as variables or columns. So when someone refers to variables or features in a dataset, they are referring to columns. Then we have observation in a dataset. If you're familiar with Excel or databases, then observations are your rows. Each observation has certain characteristics. For example, if we look at row 1, we can say that this sales observation took place in the United Kingdom. It belongs to a category of clothing, and it took place on June 30th. So all of these sales attributes are the characteristic of an observation. Our data set is made of many observations. The features or variables in a dataset will fall under one or two categories. They will either be categorical or numeric. Categorical variables take on values that are names or labels, for example, category or territory column. Categorical columns can also be referred to as qualitative variables. Sales and quantity are numeric or quantitative variables. Quantitative variables represent a measurable quantity. We can add these variables. For example, we can say that we have sold 14 quantities of clothing in the last hour. There is further distinction in numeric variables. They can be discrete or continuous. For example, quantity is a discrete variable. It falls on an exact number. On the other hand, sales is a continuous variable. It includes whole numbers and fractions. We can see the sales value printed here, and it can be 68.7 or 68.8 and so on. We can check how many observations we have in our dataset by calling the shape method on the data frame. It prints out the numbers of observation. In this case, we have 60,880 observations. And it also tells us that we have 8 variables. Let's take a look at some stats about our data. Stats are mainly for numeric variables. So I am going to only look at 2 numeric variables. We'll pass sales and quantity in square bracket. We will call the describe method on the data frame with these columns. This will print the statistics of sales and quantity. Let's examine the stats. First is the count. It tells us we have a count of 60,880 rows, and the sales mean value is 1322, and this gives us the min and the max values. We also have the percentiles, so we have the 25th percentile, 50th, and 75th printed out along with the values. Based on these percentile, we can calculate the inner quartile range. So the calculation will be 75th percentile minus 25th percentile. These are also referred as the upper and lower quartiles. So our upper quartile is 1466 and the lower quartile is 127. And the difference between them is 1388. This will come in handy later when we'll be building the box plot. If we want to know the mode of our sales column, we can obtain it by calling the mode method on sales. This will print out the mode of our variable. So these are some basic stats about our data. These will come in handy when we are detecting or removing the outliers in our dataset. Let's move on to the data distribution and check the skewness in our data. I am displaying an image of possible distribution in a dataset. In a symmetrical distribution, data is evenly distributed on both sides of mean, mode, and median. We have a positive skew if the peak is to the left of the mean and tail is to the right. And we can have a negative skew, which is the opposite of positive, with the peak to the right of the mean and tail is on the left side. Keeping these in mind, let's plot our data to check for skewness. We are using distribution plot from Seaborn, and we are passing it the sales variable and setting the bin size and the color. At the top, I am suppressing a warning as distribution plot is set to be deprecated. So let's see, out of these three distributions, what kind of distribution our data has. The visualization shows a peak on the left and we have a long running tail to the right. This is a sign of positive skew. So our data has positive skew, and we can further confirm this with a sample distribution. A dataset can have multiple peaks, and we call such datasets bimodal. Our dataset has only one peak, so it is a unimodal dataset. This is another term that gets thrown around during distribution discussion. Let's plot a histogram to prove the positive skew in our data. We'll call the hist method from matplotlib and supply it the sales variable. It shows the similar distribution with the concentration of values on the left side. Let's perform one more test and fit the normal distribution to our data to confirm our findings. We have imported the norm from the SciPy stats. We are saving our sales variable in a variable called data, and we provide the data to the norm.fit, which returns mean and the standard deviation. We plot our sales histogram with matplotlib, and from norm.pdf or probability density function, we get the p-value and plot this using PLT. I'll run the cell, and this gives us the familiar looking histogram, and we have a normal distribution line plotted on top. This confirms that our data has positive skew with the peak on the left and the tail on the right. Our data has a huge concentration to the left of the mean. Let's go ahead and move to the next step. We are going to detect outliers in our sales variable. Let's go over the box plot first. It uses the 75th percentile and the 25th percentile. These make up the box plot, with a line in the middle that represent the median. The outer limits are the whiskers as they're called. They are Q1 minus 1.5 times IQR on the left and Q3 plus 1.5 times IQR on the right. These are the whiskers on the box plot. Any value outside the whiskers is called an outlier. We will use this technique to remove outliers from our data. All the values on the right side of the line are outliers. So it seems anything exceeding 3,500 or so and going up to 28 or 29,000, these are outliers in our data. Let's take a stab at removing the outliers. We can go ahead and print the 25th and 75th percentiles by calling the quantile method and passing it the value to the data frame. Based on these, we can calculate the IQR. So those are 1466 minus 127. This gives us the IQR value of 1338. Based on these calculations, we can set the lower threshold value and the upper threshold value for outliers. We will use these thresholds to remove outliers in our data. So if we want to find out the whisker value on the right, then the formula is 1.5 times IQR plus Q3. Our IQR value is 1338, so it will be 1388 times 1.5, and then we add the Q3 percentile, which is 1466. So this adds up to be 3473. Below is our function that does bulk of the work. It takes data frame and figures out the 25th and 75th percentiles and calculate the threshold based on the IQR and returns a data frame excluding the values outside the thresholds. I will call the function with the data frame. This will take a few seconds to complete, so I'll give it some time to complete. Okay, the function call is complete, and let's plot the data again. As you can see, our box plot looks much different. Box starts from the 25th percentile or Q1, which is still 127. And this is our median line. It remains the same as well, I believe 461. However, the box plot ends at 75th percentile and it has changed. It is below 1000. Now we see a lot less outlier values as compared to before. In the initial run, the max value on the x-axis is at 25,000 and few values even exceeded 25,000. After removing outliers, our max value on the x-axis is below 3,500. It is 3473 to be exact. So we have removed all the values outside the upper threshold. Let's go ahead and print the quartiles and see the actual values. Our 75th percentile or Q3 came down to 939 from 1466. Q1 and median remain the same. However, the IQR value is also down to 811 from 1338. We can also check the new threshold values. So if we were to run this function again, it would remove any value exceeding 2157. This is the value of the whisker on the right side of the plot. Let me rerun the function again and see how it impacts the outliers. I will let the function complete. Okay, the function call is complete. We can rerun the box plot on the updated data. Now the whisker line stands at 1470 or 1480, and values above it are considered outliers, which go up to 2157. I still have outliers in my data, but we have removed 2100 to 30,000. But I'll leave it at this point. So this is how we remove outlier in a dataset. There are many different approaches to removing outlier, but this is the simple and easy to follow approach. Then we are dropping duplicate values in the dataset. We simply call drop_duplicate on the data frame. Let's do a count to see how many observations are available now. And now we are left with 27,000 after removing the outliers and duplicates. Let's also check if we have any missing values by summarizing the nulls. In the category column, we have 37 missing values. Let's go ahead and drop these. We can check again to see if the missing values are removed. This is how we drop missing or NaN values from our data set. Let's move on to univariate analysis of categorical column. Univariate simply means analysis of a single variable. We will plot the values of category variable in a bar plot by calling the plot function on the data frame .category. I will run the cell and it will plot the count of sales per category. As we can see that component category lead the way in the sales, followed by clothing, bikes, and then accessories. We are selling a lot more component than any other category, and more bikes than accessories, which is interesting as one would think that a company would sell more accessories than bikes. But this is not the case here. We can print out the actual numbers behind the chart by calling the value count on the data frame. We can also find the frequency of each category in our variable with the help of pd.crosstab. We provided our category variable and set the column to relative frequency. First, let's see the actual numbers. So I will comment out and call the tab variable. This is the relative frequency in numbers. If we want to see the percentages, then we simply divide the tab by tab.sum. I will update the data frame reference to df and rerun the cell. This looks much better. As expected, the component make up the larger portion of sales, followed by clothing. This is the relative frequency table of category variable. So this is our univariate analysis of a categorical variable where we analyze the category variable in our dataset. Let's move on to the next topic, and you guessed it, it's bivariate analysis. This is the analysis of two variables. Here we will look at two categorical variables, product category and country. I'll go ahead and update the column reference and rerun the cell. This is how our product categories are performing in different countries. Right off the bat, we can tell that we are selling a lot more products in the US than any other countries. US figures are a lot higher, as we can tell by the numbers. Then I believe it is Canada with the second highest distribution of numbers. And Australia seems to be trailing at the last place as it has the lowest numbers. We can go ahead and visualize this data. So I am going to call CT, that's the variable above, and on it call the plot.bar with stacked set to true. This gives visual representation of the frequency table above. US makes up the bigger portion of the stack across all categories. However, this is probably not the best representation of this data, as some of the slices or some of the stacks on the bar are too small. Let's try a group bar chart and see if it gives us a better way to compare the categories. Let's prepare our data. I will go ahead and reset the index on the CT variable and give auto-generated column a name. I will call it value. By default, it is called 0. I'll save this into a stacked variable. I am going to run the cell and we get a data frame with category, country, and sales count values. Let's go ahead and plot the stacked variable by using the seaborn bar plot. I'll set the X to category and Y to values, and hue will be our country. This is our grouped bar chart by categories. This is a better way to compare how categories stack up across countries. Here it is easy to compare how each category is performing as it has its own individual chart. The data still present the same picture as US makes up the huge portion of the sales. Also, it gives us an idea where we can improve on our sales operation. Let's continue with multivariate analysis. We will move to categorical and numeric variable. Let me enable the first line. We are grouping the data by category and country and getting the average sales and the discount. I'll go ahead and update the column reference and rerun the cell. Let's call the data frame to get a sense of the data. I do see average sales amount, but I don't see any discount values. I suppose discount values were present on the observations that were outliers. Anyways, let me plot this data in a chart as is, and I'll update the data frame to reference from the previous cell, which will be bi_v, and run the cell. We are displaying discount and sales against category and country. This falls under multivariate analysis as each bar is a combination of category and country, and we display sales and discount. We are using two categorical and two numeric variables. In this case, we are displaying average sales by category and company and whether we offer any discount. This gives us a clear picture of how each category is performing in different countries. For this demo, I'll go ahead and import the dataset again. I believe the discount values were dropped with outliers. We are reading the data from the source again. I'll jump down to the data transformation step of multivariate analysis. I will enable the row where we are filtering the data where discount values are greater than 0. I need to update the column reference. It will be product category and rerun the cell. Okay, this looks much better. We see some discount values in our dataset. I'll update the chart reference to D_V and update the chart to reflect these changes. Now we see some discount values stacked on top of the sales. It appears that we only offer discount on bikes category, but that's not the case. I believe the values in other categories are too small, so they don't show up on the chart. This is our multivariate analysis of categorical and numeric variables. Let's continue with sales and discount analysis and see if there's any relationship between these two numeric variables. Here we are plotting discount against sales. By convention, we plot the independent variable on x-axis and dependent variable on the y-axis. It's all about the direction of causation. Let's say our hypothesis is that the change in discount impacts sales. In months where we offer discount, our sales go up as compared to months when we don't offer discount. We can prove or disprove this hypothesis by exploring the relationship between these two variables. We will use a scatter plot and correlation test to prove this. Let's plot our data using Seaborn scatter plot. We have provided discount as X and sales as Y, with product category as the hue. And we are setting the size of the bubble with sales. By looking at this chart, we can conclude that there is no strong relationship between discount and sales. At 0 discount, we see a high volumes in sales. In other cases, we have offered substantial amount of discount on our items, but the sales volume is not that high if we compare this to a lower discount amount. So we can conclude that the discount does not have a strong correlation and it does not impact the sales as much. We can check the correlation with Panda's core method. On the discount variable, we can call core and pass in the sales variable. This gives us the correlation coefficient of 0.17. If you want to know or print the p-value, then we can call the Pearson R from the stats library and pass in our variables. This gives us the same correlation coefficient of 0.17 and the p-value is 0. This value suggests that there is a negligible relationship between these two variables. I have a table above that explains the p-value. Our value is 0, so it's the last bullet in the table here. So per this, there's a negligible correlation between discount and sales. In sales world, the relationship between unit price and sales should be a strong one. We can put this to test. I will replace discount with unit price and rerun the cell. This gives us 0.72. It is a higher correlation than discount. We can refer to the table again and figure out where 0.72 falls. It falls under the second bullet and it indicates a strong correlation. Let me update the scatter plot and supply the unit price to visualize the correlation between these two. As our price are going up, so is our sales, which makes sense. As the price goes up, our sales amount are higher, and this suggests a higher correlation between sales and unit price. I will skip over the country's univariate analysis. However, it is available to you in the notebook and you can explore it later. And I will skip to creating a new variable in our dataset. This is referred to as feature engineering in data science world. We will extract year from our order date column. It is added to the data frame at the end. We can scroll to the right to view this new variable. I am going to graph our sales by the year. So we sum and group the sales by the year column. This is our sales through the years. We have 4 years worth of data and we can see how our sales are progressing through the years. After the first year, which is 2011, we have made steady progress in terms of sales. With each subsequent year, there's growth in sales. However, in 2014, we see a huge decline. We can further analyze the data to see why the sales are decreasing. Let's go ahead and create another feature, month_year. We are applying a lambda function and formatting the date as string year-month. Then we group the sales by this new column. I'll go ahead and extract the unique month values from the data frame. We will use this for x-axis and x-ticks on the bar plot. Then we are plotting this data with matplotlib in a bar plot. This is how our sales data looks like over months. We have a steady progression in sales since 2011. We have done very well up until Feb 2014. It seems there's no sales registered during this month. What's interesting is there's a huge surge the very next month. In fact, March 2014 is the best month in terms of sales in the history of the company. In April, there is no sales again, and May register strong sales numbers once again. This is an alarming point as we were making steady sales through the months over the course of 3 years. One thing for certain though, that we may see our 2014 yearly bar go up as we're only 5 months in the year. Therefore, 2014 has low sales figure compared to previous 2 years. However, the figures in Feb and April are significantly different from the rest of the months, and this warrants further investigation. This is what we call an anomaly detection. We have identified a rare observation. We are missing sales for 2 months, and then there's a huge surge in sales. So we go from no sales to a record-breaking month in the following month. This is alarming because you want to see steady progression in either direction in your sales, and we will further investigate this. Let's just focus on 2014's data and try to figure out why we have low sales in Feb and April, as these months do not register any bars on the plot. I have filtered out the data based on order_date.year for 2014. Data is grouped by year-month. We can see the sales amount in Feb, but it's very low as compared to the rest of the months. Jan is 669,000, but Feb is mere 1,800. There's a huge drop here. This is followed by 1.4 million. Same pattern follows in the next 2 months, huge swings in the sales. We can check the other years to see if there's a trend like this. 2012 presents a consistent sales image. So we move on to check 2014 sales and discount per category. This group data frame tells us we have done very well in Jan, and bulk of the sales is made up by bikes category, and we offer discount in this month. However, in Feb, there is no discount offered, and strangely, we didn't sell any bikes. Same is the case in April. This can be due to the fact that our customer base is waiting for discount, or we may not have had any bikes in stock. Whatever the case may be, it has adversely affected our sales. There are a few more components in this notebook, but I'll leave that for you to explore. This is the Exploratory Data Analysis with Python on AdventureWorks database. We have covered various techniques from summary statistics to uni and bivariate analysis, removing outlier, and detecting anomalies in a data set. I hope this was informative and enhanced your knowledge on the subject. Dataset and notebook is available on the GitHub repo. Link is in the description. I would recommend you pick up some of these techniques and apply them to a new dataset. Practicing plays a major part in the learning. You learn more by doing, and you may encounter issues along the way, but researching and solving those issues will serve you better in a long run. So I would say get your hands dirty, grab the dataset and notebook, and practice. This is all for now. If you like the content, give it a thumbs up, like, and subscribe. Take care of yourself, and I'll see you in the next video.